All right, let's just jump right into it. We're going to be looking at a paper with one of the boldest titles I have ever seen. It's proposing a completely new way to think about quantum mechanics, and it's basically saying, hey, what if it has the exact same DNA as Einstein's theory of gravity? Buckle up, because this is a big one.
And the paper does not mess around. It closes with this absolute bombshell of a statement. For 100 years, we've all been told that quantum mechanics is just fundamentally weird and impossible to really understand. Well, this paper comes along and says, nope, you've been looking at it all wrong. The weirdness, it's not magic. It's just geometry.
So, what is this revolutionary idea? Well, it's this. What if classical physics, relativity, and quantum mechanics aren't actually three different sets of rules? What if they're all just different flavors of the same basic principle? And that principle is all about the shape of the space you happen to be playing in. So here's the core of it, right? The paper's big claim is that the shape of your space dictates the rules of the game. If your space is flat, like a big empty parking lot, things move in straight, predictable lines. You throw a ball, it makes a nice arc. Easy. But what if the space itself is curved? Well, then that nice straight path just isn't an option anymore. The geometry itself forces things to move in a wavy, probabilistic way. And boom, that's where quantum mechanics comes from. All right, so to really get this, let's start with the familiar half of the story. We've got to take a quick look back at how Einstein totally blew up our idea of gravity using this exact same kind of geometric thinking. So you remember the old picture, right? Newton's gravity was this mysterious force pulling things together. But Einstein came along and said, hold on, there's no force. What's actually happening is that massive things, like the sun, are literally warping the fabric of space-time around them. So a planet isn't being pulled by the sun, it's just following the straightest path it can through that curved space. And that straightest possible path has a special name. It's called a geodesic. This is super important. To us, a planet's orbit looks like a big circle, right? A curved path. But from the planet's own point of view, it's going perfectly straight. It's the space itself that's curved. The geometry's in charge. Remember that word geodesic. It's key. Okay, you with me? Because here comes the big leap. What if we take Einstein's trick and apply it directly to the quantum world? What if all those bizarre quantum rules aren't just things we have to accept because they are? What if they're also just particles trying to travel in a straight line, but through a totally different kind of curved space? And here it is. This is the heart of the whole idea. With general relativity, the space is space-time, and when you curve it, you get gravity. Simple enough. Now, for quantum mechanics, the paper says the space is something called probability space. Just think of it like a map of everything a particle could possibly do. And here's the kicker. That map isn't flat. It's curved. And that curvature, that's what creates all the rules of quantum mechanics. And this gives a whole new job to one of the most famous numbers in all of physics, Planck's constant, h-bar. We usually just think of it as this impossibly tiny number we plug into our equations, but in this new picture, it's something way cooler. It's basically a geometric constant. It literally tells you how curved this probability space is. And the only reason our big, clunky, everyday world seems flat and normal is because h-bar is just so tiny. Okay, so this is where it all starts to pay off, because if this whole geometric idea is right, it means that all the weird quantum rules we've had to just, accept for 100 years, they're not weird at all. They're not arbitrary. They're unavoidable. They're simply what happens when you move through a curved probability space. So take this question, for example. It's one physicists have been asking forever. When you measure a quantum system, the odds of getting one result versus another, they always follow this very specific wave-like pattern. But why? Why that exact pattern? Why not a million other possibilities? Well, this is the rule they came up with. It's called the Born rule. And for almost a century, it's just been a postulate. That's a fancy word for a rule that you know works, but you have no idea why it works. Scientists basically had to write this formula into the theory by hand, because every single experiment said it was right, even though nobody could explain why it had to have this very specific mathematical shape. And this paper claims to have the answer. It proves something called a rigidity theorem. And what it shows is incredible. It says that if your space is curved and your probabilities have to behave normally, they can't just fly off to infinity, then the only mathematical form the probability law can take is this one. This exact cosine squared shape. It's not a choice, it's not a postulate, it's forced. The geometry makes it happen.
This table just lays it all out beautifully. The parallel is, honestly, it's kind of stunning. So let's just walk through it. Top row, general relativity. The space is space-time. What curves it? Mass and energy. And what's the effect? Gravity. Okay, got it. Now bottom row, quantum mechanics. The space is that probability space we talked about. The technical term is projective Hilbert space. It has its own rule for curvature, called the Fubini study metric. And what's the effect of that curvature? The Born rule, those wavy probabilities we just talked about. You don't have to be a mathematician to see what's going on here. The logical structure, it's exactly the same.
And what's really cool is this framework also gives us a perfect explanation for how our boring old classical world shows up. Just imagine if you could somehow turn a dial and make Planck's constant, h, go all the way to 0. What would happen? Well, the curvature of probability space would completely flatten out. All those weird wave-like quantum effects, they'd just disappear. And you'd be left with the simple, predictable, straight-line physics of the world we see every day.
So, what does all this mean? Where do we go from here? Well, if this geometric way of thinking holds up, the implications are, frankly, enormous. It could change how we approach the biggest questions in physics. Take entanglement, for instance. That spooky action at a distance that drove Einstein crazy? Maybe it isn't spooky at all. This paper suggests it might just be more geometry. The idea is that when you entangle two particles, their combined probability space gets an extra layer of curvature. And that extra curve is what we see and measure as this spooky connection.
Which brings us right back to the beginning, and to the biggest question of all. For a century, our two greatest theories of the universe, general relativity and quantum mechanics, have refused to play nicely together. But what if they were never separate to begin with? If gravity is just the geometry of space-time, and quantum rules are just the geometry of probability space, could they both be just two different sides of the same coin? Two windows into one single unified geometric reality? Now that is something to think about.